We had already spoken about what is the meaning of a function approaching a limit when x goes to a, about what is the meaning of continuity, but it will be interesting to know what sort of properties continuous functions have. Have they something interesting to tell about themselves? Some properties are very simple that we would just mention in the very beginning, that if you take f and g, two functions, to be continuous, then so is f plus g, so is f minus g, so is f g, and f by g if g x is not equal to 0 over the domain of the function. So, now we will try to give some descriptions about important properties of functions. So, we will now consider a function f defined from an interval I to R. I would say that you can take I in your mind either as open interval or you can take I as a closed interval. So, the range of f is called the image of I, fi, which is the range of f or image of I. So, f of I is the set of all f of x in R such that x belongs to the interval, either closed or open, does not matter. A very important question is this range an interval? Is this an interval? It is not so obvious. You would like it to be, but it is not so obvious, and that is why you need proofs in mathematics, that you need to really rigorously justify what statements you are making. The important result is the following, that if f is continuous, if f from I to R is continuous, that is continuous at each and every point. Remember, if it is a closed interval, then when you are talking about the continuity at the point A, then you are talking about continuity from the left side, because you only can take the limit from the right side. You can take the limit from the right side. You can approach A from the right side, and if you are talking about point B, you can approach only from the left side. You cannot approach from the other side because the function has no definition outside AB. So, if this is continuous, then f of I is an interval. This is a very, very fundamental result, truly important. I would rather say I will put a red sign around it to tell you that this result is very, 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 very important. What is the conclusion of this result? What can it give me something more? Okay, this is very interesting, that okay, the image is also an interval. So, how nice the function might be, of course, but can it tell me something more? This leads to a very, very famous property about continuous functions, and those who know some mathematics would immediately realize it. It is called the intermediate value property. Let us see what is it. This is just a consequence of the fact that an interval is mapped into an interval by a continuous function. Now, what does this say? What is the meaning of intermediate value property? So, I will write in red. So, let me now consider, let me, instead of going for open or closed interval, let me just take this, right. I just want to make one point here. you can take I as this or that, but when you want to have this thing, you have to remember that I have to consider I as a closed interval. So when you are talking about a function, you can either take this interval or take this interval. But if you want to talk about these important properties, then it is better to just concentrate on closed interval. So that is why I want to state here that I will just consider on this interval f from a b to r. So now from now on our study would be concentrated on this type of functions. This is actually a larger property. Those who know some more mathematics would realize what I am trying to say is that the continuous image of a compact set is compact, but forget about all these things. So if I is of this form, that I is continuous, then fi is an interval if I is given like this. But if I say a to b, then I cannot talk about this, I cannot conclude this result, right. So for me the interval from now on should be just this. Taking this interval IAB is much more easier when you are talking about derivatives. There are reasons for it which will not go, but for me, when I am talking about continuous function, I am only talking about this interval. So I now write this one. So this result which I said is very important, I just forgot, sorry for that, that this result holds only if I is given in the form of a closed interval, right. Then this fact is a very clear fact that if this is an interval, then fi is an interval, of course is an closed interval, rather is a closed interval. I want to make it more clear. So is a closed interval if I is this. This is of fundamental importance. Once that is done, so we come to this. It says, okay, let us have a function like this, and let lambda be element of R such that lambda lies between f and b, because I do not know whether f a is bigger or f b is bigger, whatever it is. Lambda should lie between f a and f b, whichever is bigger or smaller, that is not a big issue. Lambda lies between f a and f b. Then there exists xi belonging to the open interval a b, because you know at f, because I want lambda to lie strictly between f a and a b, there exists xi between a and b such that f of xi is equal to lambda. So suppose if a is strictly less than f b, then I am expecting a lambda to be of this form. Lambda is this. Of course, there is no harm if you take equality. Then of course, if you take equality and if lambda is f a, then you already have a, and if lambda is, so you can say, okay, see, remember this xi, if lambda is strictly between this xi has to lie strictly between this. The reason is, suppose xi is equal to a and f of a is that same, f of xi is equal to lambda but xi is equal to a, then this will not be a function, it will break the definition of the function. So if xi is strictly in ab and lambda is strictly in this, if lambda is strictly between f a and f b, then xi must be strictly between a and b. This is very important thing about the intermediate value theorem. This one has to keep in mind, because if you say that no, I take xi in the closed interval ab, then and if xi equal to lambda, which means you are keeping the fact that xi could be a, but then it would be f a would be equal to lambda. So f a would have two values, one is f a and one is lambda, because I have said that lambda is different from f a. So this is something very important. Okay, if you put both as equality, then you can have a closed interval. So but let us, we need not bother about f a and f b, because we know the points where the. Now this is a very important result, it's, if you draw a picture, it looks like this. So here is some continuous function. This is my B and this is my A. So this is my f of B and this is f of A. Now take a lambda which is here. So how do I know that there will be a xi lying between A and B? So how do I find from this graph that xi? So just draw a line parallel to the x axis through lambda and see where it cuts the graph of the function. It cuts it here, and then from there you drop that it hits somewhere between A and B, and this is your xi, because f of xi is lambda, because this point is nothing but xi lambda. Coordinate of this point is xi f xi, and f xi is equal to lambda. So that is the geometric interpretation of the intermediate value theorem, and that is going to happen every time. So this property leads to very important property of functions from a closed interval to R. That property is called the property of f being bounded, boundedness property. Boundedness property में let us so what do we mean by a bounded function? A function f from AB to R is bounded if there exists k greater than equal to 0 such that mod of fx is less than equal to k for all. This is the sign for all. I am giving this sign and I am possibly not making it amply clear. This actually means for all x which is lying in the interval AB. That is the meaning of function is bounded. A very important conclusion which comes out of this intermediate value property is that and the fact that intervals are mapped to intervals, that if, again it has to be a red mark property, if f is a function from AB to R, then f is bounded on AB. That simply means exactly this, the fact that we have just wrote. But this has a more deeper consequence. So we will not now come to tell you some stories about maxima and minima. Tomorrow's in the next week's first class on limits and continuity would be rather about examples. But today we will talk about something very, very important. So x element of AB is said to be a maximizer of f over AB if f of x is less than equal to f of y for all x element of AB. If you want to look smarter, then you can write f of x supremum of fx fy y element of AB. Similarly, you can talk about a minimizer. The function value, sorry, here I made a mistake, I said a maximizer. So, means this function value fx is bigger than all possible function values at all other points. So, x is a maximizer over AB if the function value at fx, that is fx, is bigger than the function value at any other point y in AB. Now, x element of AB is said to be a minimizer of f over AB if f of x is less than equal to f of y, this is greater than or is less than for all x in AB, that is the function value at x is smaller than the function value at any other point in AB. So, what is great about the maximizer or minimizer? So, maximizer or minimizer may not exist. Now, you see, you might wonder that if the statement that I have written that if f is from a to b to r, then f is bounded. Of course, remember we are only talking about continuous functions. So, this f of a to b to r is continuous. So, maybe I am not very clear on this. So, let me write it down. If f from a b to r is continuous, then f is bounded. So, okay, that is so, but remember we are only talking about continuous functions, we are not talking about any other functions. So, if I miss also continuity in this statement, because as I go on along with the flow, forgive me for that, but take f to be continuous. All statements here pertain to continuous f, it does not pertain to discontinuous f at all. So, what is our conclusion? Why I need to talk about a maximizer and minimizer? Basically, then you know that at what point the maximum value is there, what point the minimum value is there. So, does it happen when you have a continuous function from a b to r? If f from a b to r is continuous, so if a b to r is continuous, then there is a maximizer and a minimizer. Maximizer and minimizer in the sense we have just defined. There is a maximizer and a minimizer. But this is not true if I, for example, want to talk about a function from a non-closed interval to R. That is, take a function f from say 0 to plus infinity, this interval, when the whole real line other than 0, all the positive numbers to R, and fx, so of course is not a closed and bounded interval, fx is equal to e to the power minus x, then the infimum of f when x is varying over 0 to plus infinity, where of course 0 and plus infinity is of course not a number. So, on this interval, open interval, then the infimum value is 0, but there is no maximizer or a minimizer. So, infimum value is 0, and in fact you can check out the supremum value of fx as x goes to is in this interval is e to the power 0, which is 1. But in this interval 0 to plus infinity, where 0 is excluded from the interval, there is neither x, no x for which fx the value is 1, or no x for which fx value is 0. So, this closed and boundedness is a very important concept. So, you have to understand that we are only talking about functions of this form, continuous functions of this form. Note, in this interval 0 to plus infinity e to the power minus x is actually a continuous function. So, with this little examples and list very important, we have learned some very important properties of continuous functions. We are going to close our discussion, and in the next week we are going to start giving examples of what we have just learned and then move on to derivatives. Thank you.